Okay, we're going to talk about continuity now, and to talk about continuity, continuity is an adjective that defines function, or describes functions. So we're going to have to talk about functions a little bit. And continuity and limits are really closely related, so we're going to talk about limits of functions first. I guess not exactly first. That'll be the number one thing on the list. The number 0 thing on the list is what's a function, just for a review. So a function is a mapping from a domain, let's call it X, to a range Y, where every element X in X has a unique element in the range Y associated to it. Okay. So just by definition, everything in X has to have an output associated to it. Not everything in Y is used. Well, not necessarily. Okay. Just kind of keep note of that. So some notation. F maps X to Y, and X gets mapped to f of X. This is sort of function notation we'll see used, or part of it, maybe just the top line, we'll see used. This guy is the domain, this guy is the range. I don't think the book says this, but sometimes this is called the codomain. Okay. So let's see an example. F maps the real numbers to the real numbers, sending X to X squared. This is a function. Takes real numbers. Every real number I can put into this, and I can get a real number out when I square it. Like I said, not everything in the range gets hit, but everything in the domain can be put into this function. So another example, maybe a non-example. F maps R to R, sending X to 1 over X. What's wrong with this? We can't divide by 0, right? So this isn't quite right. Right? Not everything in the domain has an output associated to it. I could fix it by defining where 0 goes, or I could fix it by taking 0 out of the domain. And so what we might write instead is f maps negative infinity to 0 union 0 to infinity to the R. X gets sent to 1 over X. That would be one way to fix it. And so we've got to kind of be careful about what our domains are, and that's why domains, finding the domain of a function is kind of important. Finding the range of a function is kind of important too. But finding the domain is a little bit more important, because we're okay with leaving things out of the range. And we're okay with leaving things out of the domain, but the thing we're not okay with is putting extra things into the domain. So let's now think about limits of functions. Okay, so this is kind of a long definition, and I'm going to kind of break it into parts and draw some pictures for the parts as we go through it. So suppose x dx and y dy are metric spaces. So if we're going to talk about continuity, we kind of have to have an idea of what it means for two pieces, or two things in the domain to be close together and two things in the range to be close together. So the domain has to live inside of a metric space so I can measure distances, and the range has to live in a metric space so I can measure distances. So x isn't going to quite be our domain though, because we want to make sure that we haven't included things in the domain that don't make sense, like the 1 over x function. Okay. So we're going to take a subset of x, and the book calls it E, so we'll take E to be a subset of x. And f is going to be a function from E to y. Okay, so now we've kind of got our setup. So let's draw some pictures here. Let's say that this set is x, and maybe I've got this set here, which is E, and f sends it over to y, and maybe it's not necessarily continuous, but maybe it kind of sends, like the 1 over x function breaks it into two pieces, right? On the left half you've got the curve that kind of comes down like this, and on the right half you have the curve that kind of comes up like this. So let's kind of make these guys into blobs, and we'll call these things together f of E. Okay, so I've got stuff in here and in here, and f takes all of the things from E and sends them into one of these two blobs. All right. So that's just going to be kind of our example function. Now, we say the limit of f of x equals L as x approaches a. That's kind of our statement if, well, what do we need here? We need something to do with inputs approaching a value, and then we need something to do with outputs approaching a value, right? Okay, so if A is in the closure of E, let me put that in white. So I've got this point A, which is in the closure of E, and whenever we get close enough to A on this side, if I get close enough to A, I'm close enough to this L value on the other side. We'll say that this is L on that side. And whenever epsilon is bigger than 0, we can find delta bigger than 0, such that for all 0 less than the distance in x x comma a less than delta, we have for all x we have that the distance from f of x to L is less than epsilon. Okay, so let's go to our picture again here. Let's make this L green. This point's green. Okay, so what I want to do is go through this. A doesn't necessarily have to be in the domain. Right? Okay. And so E is the domain of our function. A just has to be a boundary point of that domain. Like 1 over x, I could take 0 to be what we're approaching in the limit, and that's not a problem even though 0 is not in the domain of 1 over x. Alright, and then let's look at this epsilon. Go with epsilon's bigger than 0. So epsilon is a range thing. So I want to draw a circle around L of size epsilon. So this is an epsilon radius. Okay. And then I want to know that if, let's go with a yellow, a delta thing. If my input values are close enough together, input values are within epsilon, the output values lie within that pink circle. So what I need to do is I need to find a yellow circle here. So all these things here, when they map over inside of E, we don't know what shape they'll be, but we want the shape of all of those things to fit inside of the pink circle. So if I hit this yellow circle with the function, it sends it over to here inside the pink circle. And I want to be able to do that no matter how small I draw this pink circle. I want to find a smaller yellow circle that maps inside the pink circle. Okay, let's see an example of some real numbers and how it's going to work. So let's look at f of x equals x squared minus 4 over x minus 2. Okay, this function isn't defined on all of the reals, right? I can't plug 2 into this number, or into this function. I get division by 0 if I try. But we can try and take the limit as x approaches 2. So we'll find the limit as x approaches 2 of x squared minus 4 over x minus 2 equals, well, it's going to be 4. If you do the arithmetic, you get a difference of squares on top, divide by x minus 2, cancels out part of the difference of squares, you get this. This looks like x plus 2 everywhere except for 2. So if we want the limit to exist, it should be at 4. Let's see how that all works out mathematically though. And to do that, let's draw a picture. This graph, I probably don't need that much of a horizontal line. This graph, it's going to look like it has a hole in the graph right here at 2, 4. It's going to have slope 1. And so the graph of our function looks like this. And we had a pink circle. It looks like our limit is going to be right here. And so if I go epsilon out from the limit, what I want to know is, what do I have to restrict the domain to around 2 to stay within this pink band? Right, part of the graph is inside the pink band here. How far in my domain can I get away from 2? Here's 2. How far left and right of 2 can I be and stay within that pink band, that pink bubble? Well, it looks like I can come down to about there, and I can go up to about there, and this is going to be what my delta is. Okay. So if I want to stay within the pink band, I have to stay within the delta band, the green band. I want everything inside this function to be inside this little rectangle here. So now let's take an arbitrary epsilon and see in terms of that epsilon what delta is going to have to be, and that's going to be how we're going to prove that this limit's going to be 4, right? So let epsilon be bigger than 0. Then, well, our slope here is 1. That's one way we can kind of do it without a bunch of scratch work on the side. Let's kind of do the scratch work though. So we want x squared minus 4 over x minus 2 minus 4 less than epsilon. And we want to compare that to 2. So let's see what would happen here. Let's multiply both sides by absolute value of x minus 2. And what we get is, we want the absolute value of x squared minus 4 x minus 2 less than epsilon times x minus 2. Okay. I can factor out an x minus 2 on this left hand side as long as x isn't equal to 2. We're good with this. So let's take x plus 2 minus 4 in absolute value is less than epsilon, or x minus 2 in absolute value is less than epsilon, which tells me the distance that x has to be from 2 is also less than epsilon. This gives me my delta right away. So delta equals epsilon. Then if delta is less than epsilon, we have, so here was our scratch work to figure out what delta had to be. So we let epsilon be bigger than 0. If we let delta be less than epsilon, we have that whenever x minus 2 is less than delta, which is less than epsilon, we're going to kind of reverse our scratch work. We get x plus 2 minus 4, still less than epsilon, multiply everything by x over 2, or x minus 2. And then divide by absolute value of x minus 2. which is what we wanted to prove. And we're okay with doing all of this because up here in our definition of the limit, there was a reason that I needed this 0 less than. I can't actually use the point A. I need the distance from x to a to be positive, so we can't use A. And that lets me divide by x minus 2 because I can't have x equal to 2. Which means we can kind of avoid the division by 0 that way. Okay, let's do one more example that's maybe a little trickier. And this function is going to be a little bit stranger. So let's look at f of x. It's equal to x if x is in the rationals, and 0 if x is not in the rationals. So this is a function that's defined on the real numbers. Let's kind of look at a graph of it real quick. So if I have a rational number, it's going to be the x values. So I'm going to kind of get this dotted y equals x line. But I also, here, let's graph this in a different color so you can see it show up on the x-axis too. So I got this dotted diagonal line. This is for the rationals. These are, say, q, q. And I also have all of these 0 values on the x-axis, where these are, say, irrational zeta or z, comma 0. So rationals and irrationals. All right. So let's see, does the limit as x approaches 0 exist? Well, if we draw our little picture here, and if I'm focused at x equals 0, so if I'm focused on this pink line, it looks like I could kind of box everything in as long as I'm focused in right at 0, right? So let's think of that as our limit, probably, that the limit is probably going to be 0. 0. Okay. Now, what we have to do is I have to go up epsilon and I have to go down epsilon, and I have to see how far left and right do I have to go to fit everything inside of this epsilon band. So this epsilon band goes out this way, all the way out. How far left and right can I go to make sure that I'm within this pink area? Well, I can go left that far, and I can go sort of right that far. And again, it looks like my slope is 1, so I can probably go epsilon that way, and I can probably go epsilon that way. And that's going to be true for this case. So let's prove that this limit is equal to 0. So limit f of x, x goes to 0, equals 0, since given epsilon greater than 0, let delta equal epsilon. Then if x Well, minus a in absolute value is less than delta and bigger than 0. We have that f of x equal to x if x is rational and 0 if x is irrational. That absolute value of f of x minus 0 equal to the absolute value of f of x is less than x, because it's either 0 or x in absolute value, is less than epsilon. Right, it's less than delta, which is equal to epsilon.